So it's the last talk in this course. And so today we will have a look at the problem of the determination of the reachable states for the linear Cordova-Doris equation. I think I will skip the part about the linear Zakharov-Kuznetsov equation because I don't have enough time. And finally, we will have a look at the problem of the exact controllability of first semilinear heat equation, and next I will talk about some work in progress about anisotropic 1D equation. Okay, so let's go to KDV. Here we are. And so I will present a joint work with Philippe Martin, Yvonne Riva, and Pierre Roujon, which is published in Science Journal Control in Optimization in 2019, about some determination of reachable states for the linear Korteweg-de Vries equation. So what is this equation? The Korteweg-de Vries equation actually was introduced at the same time by Boussinesq and by Korteweg and de Vries as a model for the propagation of small amplitude water waves. And it is a very simple equation. You have some three-order derivative in x, one derivative in time, and you have some nonlinear terms. And due to the balance between the nonlinear term and the dispersive term, you can have solitons. Okay, so it's a very nice equation. And its world posedness was investigated by many people, including Temam, So, Cato, Koenig, Pons-Vega, and Bourgain, who was the first to prove the global well posedness with initial data in L2, Linares, Tau, and many others. And for the control of this equation, the first contribution is due to Russell and Zhang in 1996 for the nonlinear equation, and for the linear equation, the contribution goes back to 1993. Okay, so I will just remind you some old now result about the boundary control of this equation. So you have some equation of order 3, so you can have 3 boundary terms, natural boundary data. So one at 0 for y, one at capital L for y, and one for yx at capital L. So that's a very natural boundary conditions that you can put to your equation. Okay, and so as before, I will say that the equation is exactly controllable if for any y0 and y1 you can find some boundary control among u, v, and w that steers your system from y0 to y1, and when y1 is 0, you just say that it is null controllable. Well, that's the usual definition. So I review very quickly the non-result. When you take W as the only control, so you control only the null-mine data at capital L. I would like to say maybe that you consider your equation for x in the interval 0 capital L. It was not written, but it is of course what we do. So when you control yx, so the derivative of y with respect to x at x equal capital L, and if you assume that the other boundary data are 0, then I proved in 1997 that the linear system is exactly controllable if and only if L is not what I call the critical length. And Jean-Michel Coran has talked about this phenomenon in his lecture. And you can compute explicitly this critical length, okay? And when L is not a critical length, you can as well control the nonlinear equation. Okay, so with one control, is quite easy for yx. When you take as only control u, that is, you control y at x equals 0, and for these two boundary data, you put 0, you have different result. What you can prove is the null controllability. And I proved it in 2004, and it was revisited by Glass and Guerrero in 2008 in different spaces. And for that, you need to prove some Carleman estimate. So it's similar to the heat equation. And you have at the same time the controllability to the trajectories. But the exact controllability was to that an open question, okay? And when you take now only V as a control, the system is exactly controllable for L, which is not critical. It is proved by Glass and Guerrero, and they prove that you have a set of critical lengths, which is countable. Okay, and so in the second case, when you have just a null controllability, actually you have to prove a Carleman estimate for the KdV, and it can take this form. So it's similar to the Carleman estimate for the heat equation, actually, in dimension 1, when you have only one exponential. Okay, and you can prove the existence of some convenient weight, psi, and phi, such that you have this kind of estimate, and you need that. Okay. Now, what we would like to do is to describe, in some sense, what are the states that you can reach when with only one control at the left. Okay. Okay. And so for that, we need something different. So we will use the flatness. Okay. And to make the exposition easier, actually, we will work not on the domain 0 capital L, but in the domain -1, 0, because actually we should have to make expansion, power expansion close to 0. So it's more convenient for the notation to assume that you have these two boundary conditions at x equals 0 at the right, and the left correspond to -1, okay? Okay, and so actually we'll only deal with the linear equation for the time. Here I will not give the result for the linear equation, but at least for the linear equation we have some work to do. It's not so easy, and so we have some coefficient A. In practice, A is 0 or 1 in general. So first things that we can do with the flatness approach, we can recover the null controllability for the linear equation. So without Carleman estimate, we can make it without Carleman estimate, and we can be more precise in the sense that we can build a control input U, which is in some Gevrey space. So it's very regular, okay? And it can be made explicit in some sense. And so we obtain this result with S between 3½ and 3. And so we recover the null controllability of the linear equation this way. Okay, so now let us have a look at the reachable space. And so we have to introduce some space. So first we introduce the operator, the linear operator corresponding to the derivative in x in the KdV equation. So they correspond to this part. Okay, so we introduce these operators that we denote by P. And if you assume that you have a smooth solution of the KdV equation, when you look at what happens at x equals 0, of course, y is 0, but if y is 0, all the derivative with respect to time should be 0 as well, of course. But when you take one derivative in time, it is equivalent to apply p to y up to the sign, okay? So p applied to y should be 0 at x equals 0, and the same is true for p to the n, because the derivative of order n with respect to t of y is 0 at x equals 0. So it means that if you have a smooth solution of the KdV with this boundary condition, necessarily Pn applied to y should be 0 at any time, actually, for any n. And the same as though for Pn applied to y with, in addition, a third derivative with respect to x, because of this. So this condition should imply this, actually, for any time. Okay? And so it means that the state that you can reach should satisfy this boundary condition at x equals 0. It's a consequence, actually, of the boundary condition for which you don't have any control. So it's a consequence of that. And it's a sort of compatibility condition that you have to impose. And so For the space that we consider, we consider the space of functions that are at least continuous on the segment -1, 1. Then this state Y are actually the restriction to -1 of a function which is defined on a big ball and which is holomorphic on the ball of center 0 and radius R. So H means holomorphic in this slide, okay? Holomorphic on this ball. And in addition, you impose all these boundary conditions. You have infinitely many conditions at x equals 0. And the result you obtain is the following. So assume, A is a coefficient in P. You consider any time capital T, and R should be large enough. Actually, it is related to your coefficient A by this relation. And pick any y1 in this space, then you can reach it from 0. So you can reach it by means of some control input U, which is in the space G to the 3. And also, okay, you can say that the trajectory is in the Jaurès space G13. So some instance of a function that you can reach, actually any polynomial function of this form, that are expressed as a sum of power of the form x to the 3n plus 2. But although this function, at first sight, you can think that it takes a complex value, but actually you can see that it takes real values. So it is, of course, analytic on C, so it does not have any pole. And this is a graph of this function. And what you can see is that, okay, it is 0 at 0, its first derivative as well, but at x equal -1, it's not 0. So it is not a solution that corresponds to the free evolution of KdV, for which for the free evolution, you should have y at x equal -1 should be 0. So we obtain something which is much better than the controllability to the trajectories. This is, okay, a good instance for that. So, and you can combine, of course, the two results. So the null controllability plus the result about the reachable states, and you can combine both. And so starting from any initial data in L2, you can reach any data Y1 in the previous space, provided that R is large enough. So one idea about the proof of that, so we have to prove some flatness property for the KdV equation. And so we can solve this ill-posed problem about x equals 0. So it's a Cauchy problem in X. We can solve it. Here we have two boundary data that are 0 and one boundary data which is not 0, which is Z. And we prove that when Z is in the Jaurès class GS with S less than 3, you can prove the existence and uniqueness of some solution in this class. Okay, so to prove that, this is a usual procedure. So you expand it, at least formally, this way, where Gi are generating function, and the generating function are defined this way. So this is G0, so the first function, and the other one are defined by induction. So this part, you can make it formally, but of course you have to prove the convergence of your series, and the key is to prove a good bound of the function Gi, and we obtain this one. And of course you have to prove it by induction, and it is in-house to make this series converging. And okay, we have to prove a smoothing effect. So I remind you that for the heat equation, you have a natural smoothing effect. We saw also that for Schrödinger equation, when the initial data is as a compact support, we have a smoothing effect. And here we will prove the smoothing effect, which tells you that if you consider a solution of the linear KdV equation with homogeneous boundary condition, if you start from L2, actually, the trajectory will be infinitely smooth for positive time, and actually it will be in this Jaurès space. So with the regularity 1/2 in space and 3/2 in time. So you have actually something like that. And to prove that, actually we proceed this way. So we use at the beginning the classical Kato-smoothing effect for the KdV equation on a bounded domain, which tells you that if you have some initial data in L2, actually it is L2 in time with value in H1. It is expressed this way. And you have also energy estimate, which tells you that if you are in some sublayer space HP, you stay in the same space, HP with the good boundary condition that I will not precise, you will stay in the same space. So combining these two properties, you should arrive to that actually. So you can quantify the dependence in T in this thing. And now you have as well this kind of estimate. And so you can pass from HP to HP plus 1. And also, actually, you can pass from L2 to H3, which is equivalent to P applied to L2, P applied to Y in the L2 norm, more or less. And you have to pay is that you have to divide by T to the 3/2, okay? Because you use these things 3 times. And now the trick is the following. So you have some interval 0T, you split it this way. And if you compute the L2 norm of Pn of y, you can estimate by this in terms of the L2 norm of Pn minus 1 of y at some previous time, and you pay with that. And you continue, and and finally you arrive to this, okay? So you can express this thing in terms of that, and now, you have exactly the coefficient that we had in the previous estimate. So I go back. We had this thing, okay? We obtained this thing. Well, so it is proved at hand, completely at hand. Probably it's not sharp, actually. We guess that the sharp regularity should be this one, but for the time being, we didn't prove it. Just to tell you that on the real line, you can prove it. So similarly to what we obtained for Schrödinger equation, if we consider the KdV equation with A equals 0, if the initial data is L2 with a compact support, we can prove that we have this regularity, which is probably the sharp one. Okay. And next, so we can extend the flatness property to the limit case S equals 3. So it's similar to what we had for the heat equation. So S equals 3. So you make this assumption for the derivative of for Z, and you can obtain a trajectory in this Joubert space G13 for this ill-posed problem. That is a Cauchy problem in X. You can prove that exactly the same as for the heat equation. And we use actually Borel-Ritz theorem. It's the same as the Borel we use for heat, the heat equation. Actually, we had some general statement, and we can use it as well. Okay. So this was for KdV. I will probably skip this part. So Zakharov-Kuznetsov, I will just tell you what is the equation. So now it is an equation in a dimension n equal 2 or 3 in space. So we have many derivatives in space. So we have the Laplacian, which is applied to ux. So it can be seen as some extension of KdV, but to the dimension n. And just to say that we were able to apply this flatness approach to control this equation on this domain. So we did it in dimension 2. It is a joint work with Bochen. And what we did is we control u on at x equal -1. So on a part, we have a square. Actually, we work on a square, and we apply the control on one side, the left side of the square, this way. And we applied the flatness approach, and we were able to obtain both a null controllability result. Okay, the first thing is a null controllability result. And after, we were able to obtain also a space of reachable states. I will skip this part, it's a little bit technical. Actually, it's more technical than for KdV, but the idea are almost the same. Okay, so now I proceed to explain you what are the results for the exact controllability of nonlinear PDEs. So this is the last part of my talk. So I will first show you so some result obtained by Camille Laurent about exact controllability of semilinear heat equations. Okay, so of course everybody knows that by using Carleman estimate, you can prove the null controllability or the controllability to the trajectories of nonlinear heat equation. That is, heat equation with nonlinear low order terms. But here we are interested in exact controllability result. Okay, and for that, of course, you have to work in space of analytic function, thanks to, or due to the smoothing effect. So, and we work in dimension one. Even in dimension one, it's not completely easy. And so, okay, what we want to do is to derive the local exact controllability in the space of analytic function for this heat equation. So this heat equation, and we had nonlinear terms. F is nonlinear. So you have nonlinearity in x, y, and yx. Okay, and for the moment, so you can have two controls. So the domain is -1, 1. So you have some control input at x equal -1 and another one at x equal 1. And you start from some initial data y0. Okay. And here you assume that f is analytic. Actually, it's analytic in the neighborhood of 0, 0, 0. It can have poles far from 0, 0, 0. It's possible. And so typical example are, okay, first, this one, so it's a linear equation. So it's a linear equation with some potential function phi, which is assumed to be analytic. So it's not any potential function. So it cannot be singular as in the first part of my talk. Today, when we consider the parabolic equation with degenerate C, okay? So this thing here is very regular, it's analytic, okay? So it's a linear equation, but you can as well consider the viscous Burger's equation with this thing which is not linear and which is completely analytic in y and in yx, or this equation, Allen-Kahn equation, which is very famous, for which, okay, you have polynomial perturbation, okay? What is important is that in our result, we don't have a limitation, any limitation about the magnitude of the phi in any norms. It can be as large as you want. It is not limited. So it's not a perturbative result. This linear part can be as large as you want, okay? So what we assume for f, so f, as I told you, is analytic. So you can expand it as a power series in all the variables. So x first, the spatial variable, but also y0 and y1. y0 stands for y, and y1 stands for the first, for yx, that is the derivative of y with respect to x. So it can be expanded as a power series. And of course, we have to make some assumption about the coefficient, and you assume that the coefficient are bounded like this. Well, it's classical to have this bound when these bounds are related to the radius of convergence of your series. And so you have three radius, one with respect to x, which is b0, one with respect to y0 and y. B0 correspond to y0, B1 correspond to y1, and B2 correspond to x, sorry. Okay, and okay, more or less, all of three have to be larger than 4. So B2 has to be slightly larger. Okay, but it's almost 4. So you have to make this assumption, which means that the pole, F can have poles, but they have to be at some distance of the origin. Okay. At least at a distance larger than 4, more or less, okay? But M is, you don't have any limitation for M. M can be as large as you want, okay? No limitation for that. So now the result we obtain is the following. So I have to introduce some space. So the space RC, when you consider the function y defined on the interval -1, 1 with value in R, and you assume that y can be expanded as a power series. on these intervals, that it means that actually y is analytic. And so it is written this way is more convenient because in this way, an correspond exactly to the derivative of order n of y at x equals 0. So that's just the reason for which we add the factorial n in the denominator just for convenience. Okay. And for an, we have this band. So you have two numbers that play different role. R correspond to the radius of convergence. Okay. The radius of convergence. So we assume that R is larger than 1, so that this series is converging. Okay. No problem with the convergence of this series because the radius is larger than 1. And C, you have the number C that appear here. And C is in some sense, quantification of the magnitude. In some sense, it is like a norm. It is like a norm. Later on, I will make a connection with this definition and the definition of RD space. So RD space is the set, the space of holomorphic functions that are in L infinity. So it's more or less connected to the L infinity norm. I will make the connection later on. So you can express a result actually in RD space as a classical local null controllability in RD space. So what we assume in the joint work with Camille Laurent is the following. So we assume that R is larger than R0, which is denoted, which is this number, that is almost 4 and it is slightly larger than 4. And you assume that B2 is larger than this number. Then you have some number C, which can be small because it's local controllability result, of course, because you have a nonlinear equation. And such that if you take initial data and terminal data in this space corresponding to this C, so R is completely known in some sense, but C is, it has to be small, but it is, we don't have a precise knowledge of it in this statement, but we know that it does exist. And for this data, you can find some control input, H-1 and H1, such that when you apply this input and when you consider the solution of this equation, you arrive to y1 at the time capital T. Okay, so it's local exact controllability result, local in the sense that C can be small in time capital T. So I will proceed to prove that. Actually, there are mainly two steps. So the first steps, in some sense, replace the flatness approach. What we prove is that, okay, we can investigate the Cauchy problem in X, what I called before the ill-posed problem. So we solve this Cauchy problem in X, okay? And what is important is to obtain actually global solutions, that is solutions that are defined for X in the interval -1, 1. It's actually, when we go back to the literature about this kind of problem, so we have the classical contribution by Nirenberg and Nishida, but they prove local well-posedness. So that is solution for X close to 0. But here we need to have a solution defined on the whole interval -1, 1, okay? So, okay, we have to modify slightly the things. So this is the first part, okay? In some sense, it's a result in analysis. It has nothing to do with the control. And next, we need something which is new. It's the study of the relationship between the derivative in time and the derivative in space of y at the point 0 capital T. So at x equals 0 and at the time capital T. So you have to investigate what are the relationship between this, what we call jet. The jet is the sequence of all the derivative up to infinity. So here you have the derivative in time, here you have the derivative in space, and here you have a mix of both. So you have all the derivative in time plus one derivative in space. So we have to make a connection between both. And this is the idea. So let us have a look first at the first step, so the Cauchy problem in X. Okay, so we consider this problem. So it's a heat equation with nonlinear terms like this. And you have two boundary data at x equals 0, and you want to find the solution on the whole interval -1, 1. And the result we obtain is the following. So you pick a function f as in the main theorem, so with the assumption I did before. You take r larger than 4, then you can find a number c such that if your boundary data G0 and G1 are like this, so they are Gevrey of order 2, but C has to be probably small in house, okay? Then you can find a solution of this Cauchy problem in X for all the X in -1, 1, and for all the time T in the interval T1, T2. And in addition, you can say that the trajectory that you construct is in the Gevrey space G1, 2. That is, it is of Gevrey regularity 1 in time, in space, and 2 in time. Okay. So how to prove it? So it is not proved by using a contraction principle in some Barnard space. Actually, we need to use a scale of Barnard space. That is a family of Barnard space composed of Gevrey function. I will not give the definition because it's very technical, but I will just introduce maybe this new tool for you. So you have a family of Barnard space indexed by S, and S belongs to the interval 0, 1. And you assume that you have the following. So you have embedding. XS is embedded in XS prime if S prime is less than S. Okay. And in addition to that, so embedding is continuous, and the norm is at most 1. That is, the XS prime norm of F is less than the XS norm of F for F in XS. So, for instance, one model is the scale of Sobolev space between L2 and H1. Okay, so you have all the HS between L2 and H1 for the interval 0, 1, and you can obtain something like that. Okay, so when S is larger, you have more regularity. So H1, of course, is included in L2. Okay, so there's the extreme. So when S is 1 and S prime is 0. But unfortunately, we will not work in the scale of Sobolev space. You have to work in the scale of Gevrey function space. Okay, and now we had to prove actually some abstract existence theorem. So typically, so what we consider is this equation. Actually it is some PDEs. So the derivative in x of u is t of x applies to u of x, but t is a nonlinear operator, and it can have some derivative inside. Okay, so we can have loss of derivative. So u0 it will be in the smoother space x1, and you will obtain solution which is not in x1 at the end. Okay, and so we have a family of operator, nonlinear operator, with possible loss of derivatives. I mean, you can have some derivative with respect to x inside, of course, because we have to apply to this. Here you can have derivative in x. Okay. Okay. And actually, this result is very close to a result obtained by Nirenberg and Nishida, but our main contribution is to obtain a global solution. So we have solution for x between -1 and 1. So the precise statement is the following. So we assume that the family Tx of nonlinear maps from of nonlinear operator, are maps from xs to xs prime for any S prime less than S, with S less than 1 and S prime non-negative, okay? And so it expresses the fact that, for instance, you can have some operator from H1 to L2, so you have a loss of regularity. So typically, if you have a derivative with respect to x, but of course, here it's more abstract. And you have to assume this estimate, so epsilon appears in these things. And so you divide by S minus S prime. So when S and S prime are very close, this thing is very large. So you have this estimate, also estimate for the difference. Okay, so it's quite similar. So you assume that. And you assume that also for U and V in XS with a norm which is less than some D. Okay. So this is are your assumption. So if you assume all of that, you can prove the existence of some eta, which is small and strictly positive, such that if the initial data in the x1 norm is less than eta, you can find a solution of your integral equation. And of course, this equation will give you this thing. So you will solve your Cauchy problem in some space x S0, where S0 is not necessarily 1. It is less than 1. So it's some number between 0 and 1. Okay, and so we prove this abstract result, and after we use it in our problem. So a few words now about the jet analysis. So what is the issue? Okay, so if we consider the simplest model of the heat equation, the linear heat equation, so you have the yt equal yxx, okay? When you consider n derivative in time of y, so you apply it n times, and you see that the derivative of order n in time of y is the same as the derivative of order 2n of y in x, the same. Okay? So this thing gives you this thing, and you can as well apply one derivative in space, and you obtain this equals this thing. So it means that the knowledge of all the derivative in time and all the derivative in time plus one derivative in space is equivalent to the knowledge of all the derivative in space. So you have a one-to-one correspondence between this jet and this jet, okay? But it is a linear case. For the nonlinear heat equation, so when you have additional term, even if they are linear, actually, when you take derivative, you are more and more terms, okay? It's more and more complicated. And of course, we don't have this relation anymore. It's much more complicated. But what we can prove is that we have still a bijection. We have a one-to-one correspondence between, so the jet, so the sequence of all the derivative in time, at the point 0t, so for x equals 0 and t equal capital T, and all the derivative in time plus one derivative in space. So the knowledge of this thing is equivalent to the knowledge of all the derivative in space. Okay, so this is what we call the jet analysis. So, okay, so you consider derivative in time or derivative in space, and okay, you can pass from one thing to the other thing. Okay. But it's not sufficient to have a bijection. We need to quantify this because we do analysis. And okay, assume that you have a f like in the main result. You pick a solution which is infinitely smooth. Okay, so it satisfies this nonlinear heat equation, and assume that you know that all the derivative in time. In space of y at the point 0t are less than this quantity, so c factorial n over r to the n, with r larger than 4 and c small. Then from this assumption, you can deduce that the derivative in time are bounded this way. Of course, for the linear heat equation, this will be trivial, but here we have the nonlinear term, so we have to be careful, and we can prove that, okay, we have what we expect, so that is some constant which will be different from c prime times the good term here, so 2n factorial divided by r prime to n, where r prime is less to r, so we have some loss. But what is important is that c prime tends to 0 with c. Okay, we need that in the analysis. Okay. So let us complete this talk with the problem of the exact controllability of anisotropic 1D equation. So it is a joint work with Camille Laurent and Yvonne Riva, and it is in progress. We are checking all the things, and it will be submitted soon. So the equation we consider is the following. So it is some extension of what we did before for the heat equation. And we consider this equation. So this thing is a principal part for instance. So zeta of j are constant coefficient, so it is a linear part here, and we have m derivative in x. The maximal number of derivative in x is m, capital M. And we can have n derivative in time, okay? And what we assume that n is less than capital M. So for the heat equation, capital N is 1 and M is 2. For the KdV equation, N is 1 and M is 3, okay, and so on. But we can have N larger than 1, but the main assumption that N is less than M, I mean you have more derivative in time, in space, sorry, than in time. You have more derivative in space than in time. Okay, this is the main assumption. And you can have nonlinear terms with derivative in y, in x up to the order m minus 1. So for the result we will obtain, we can apply it to many equations. So first KdV with now the nonlinear terms. So here n is 1 and a capital M is 3, and this guy is in these terms. Also this equation where n now is 2 and m is 4, so this is called the good-bad Boussinesq equation. Actually, it is the equation obtained by Boussinesq before deriving the KdV equation. Okay, and so it is called good or bad depending on the value of the coefficient you have here. So when the coefficient is plus, it is called the bad Boussinesq equation, and when the coefficient is minus 1, when the sign is minus, you have the good. Why we say good or bad, it depends actually of the well-posedness. So when the sign is plus, it's the bad Boussinesq equation because it is ill-posed in any Sobolev space. So it's very bad. For the analysis, it's very bad. But when you put a minus, it's good because it is well-posed in some Sobolev space. Okay, you have also Ginzburg-Landau, which is some extension of the Schrödinger equation. So this is a Schrödinger part, or it could be actually the heat part, depending on the value of the angle theta. And you have here some nonlinear terms with some phase as well, you see here. And another instance of where we can apply our series, the Kuramoto-Sivashinsky equation, where n equals 1 and m equals 4. So what is interesting in the result we will obtain is that we can have ill-posed equation. So we will be able to derive a control result even if the equation is ill-posed in Sobolev space. And this is interesting because in general, people prove result for the linear part, and after people apply a fixed point argument by adding the nonlinear part. But for that, of course, you need your Cauchy problem, the classical Cauchy problem in time, to be well posed. But here we can derive result even if the Cauchy problem in time is not well posed. So first instance, which is easy to understand, it is a backward heat equation. So I mean, you put the bad sign in front of the second derivative in x. So for that, if you start in L2, you don't have the well posed. But even so, we are able to obtain control result for that. That is, by selecting good control input, we are able to construct a trajectory solution of our control problem. And although you have the bad Boussinesq equation, which is just written here, and actually, if you put this term on the left, you can make a factorization, and actually, you see that you have the backward heat equation that appears in the factorization. So that's the reason for which this equation is ill-posed. Okay, so we will express our result in a space similar to the space used for the nonlinear heat equation. In this slide, I will make the connection with RD space, so I will pass some time to tell you why we use this space. So first, I introduce the notation. So I consider a radius R, which is larger than 1. So the radius is actually the radius of convergence in our Perot series. And C is larger than 0. So n of RC is a set of sequence of coefficient alpha n, such that the absolute value of alpha n is less than C factorial n divided by Rn. So it's we introduced this set of sequences before, okay? So R is a radius of convergence and C is the magnitude. And next, R of RC is a set of functions defined in the interval -1, 1, such that you can expand as power series this way with the coefficient alpha n, and the sequence of coefficient alpha n is in the space nRC. So that, I mean, you have this estimate. Well, so with this estimate, I remind you that for R larger than 1, you have the convergence of this series. You don't have any problem of the convergence for that. Okay, and actually we will express our result still by using this notation. And I remind you that R is related to the radius of convergence and C is the sort of magnitude. But now I explain why C is the sort of magnitude. And so let us see what is the connection, the relationship with RD space. So we can as well introduce the so-called RD space, HR infinity. It's a set of holomorphic functions on the ball, centered at 0 and radius R, which are also in L infinity. So they are essentially bounded, okay? It is a Banach space with the norm L infinity. It's the so-called RD space, okay? So this space is, now you can introduce a ball associated to this space. Actually, what we will do, so for our problem, so we will consider the space BRC, a function defined on the segment -1, 1, with value in R. Actually, it could be C. It can be complex valued, actually, such that there exists a function f in this RD space with a norm which is less than C, it's the L infinity norm, and such that the restriction of f to the interval -1, 1 is y. Because y is defined on some real interval, -1, 1, and f, I remind you, it is defined on some disk in the complex plane, okay? So that's the reason for which we have to play with the two functions. We have y defined on some interval -1, 1, and f, which is defined on some ball. Now, okay, the link between this and this is written this way. So this RD space, not exactly the RD space, but the restriction to -1, 1 of the ball of radius C in the RD space, HR infinity, actually is included in this space. And we will express our result in this space, okay? So we have this inclusion with the same value of R and C. And now this space is included in this space. So in the space of restriction to -1, 1 of some ball in the RD space HR infinity. And here R is smaller than capital R, and C is strictly positive. So we have this connection. So the space in which we will express our result is sandwiched between two spaces of restriction to -1, 1 of some ball of the RD space HR infinity. So in some sense, we will obtain sort of local exactly controllability in some ball of this space. Okay. So in addition to our equation, our PDE, we have to introduce boundary condition. So first, we denote the linear part. In general, it is the linear part of our PDE by P of y. So it is the first sum with derivative up to order m. And we have to introduce vector containing derivative in time or in space. So in space, you go from y to the derivative of order m-1, and for the time, you go from y to the derivative n-1. So we call it partial jet. For the total jet, you have to go up to infinity, but here we consider partial jet similarly to partial sum, okay? And so this equation, of course, you have to supplement it with boundary condition. So, and we say that at x equals 0, we don't have any control, okay? So we'll have a set of boundary condition at x equals 0 that you can express this way. So you can use this notation. You will have derivative in x up to order m-1, and B is some matrix, and so, okay, you will have a linear boundary condition at x equals 0, and the number of equation you can fix it as you want, actually, so it's not limited. You can have one boundary condition or many. It depends actually of the order of your parameters. So, okay, you assume that it is given this way, where B is some matrix. And for the other boundary condition, so you just have to take the trace of your trajectory at x equal 1. You can choose the trace as you want. And the number is capital M minus nu, where nu is the number of line of B. So the number of equation in this equation. Okay, so now we have the issue of the compatibility set. So it's quite difficult to understand. You have at x equals 0 this boundary condition. So for instance, it could be Dirichlet boundary condition or Neumann boundary condition. Okay, but from this boundary condition, as I said for KdV, you can take derivative in time, and you have also these conditions that are satisfied, because when you take derivative of 0, you have 0, okay? But now you can prove that actually from the equation, so when you have a very smooth solution of your equation, you have connection between the derivative in time of the partial jet yx, yx, which is the set of derivative y, yx up to the y derivative of y with respect to x to the m minus 1. So you have a connection. You can express this derivative in time of this jet, partial jet, in terms of the partial jet with respect to t and with derivative in space. More or less, it is the fact that, okay, you can take derivative in the equation, and these two jets, these partial jets, are not independent. It's quite natural, of course, and it's the Schwarz theorem, actually. Okay, but what is important is that, okay, you can prove now this relation in this equation, and so you can infer that actually your solution has to belong to this set. So the space of functions that are infinitely smooth in the interval 0, 1, and with this relationship, which is satisfied at x equals 0 for any L. And this is the way of expressing this condition, okay? So it means that, okay, you have a compatibility condition to be satisfied at x equals 0, which comes from the condition you take at the beginning. Okay, exactly like for KdV. Now I can express the result. So you have to introduce the number lambda, which is m over n. So the number of derivative in space divided by the number of derivative in time. So lambda is 2 for the heat equation, lambda is 3 for KdV, and we call it the Jouvray regularity. So you introduce this number. Well, it's a final number which is explicit. R hat. So when R is larger than R hat and B2 is larger than R hat and T is strictly positive, there exist some constancies that we don't know explicitly, such that if the initial data are both, so in our space R, RC that I introduced before to the n, and the compatibility conditions that I introduced in the previous slide, you have a solution of your nonlinear PDEs which satisfies the homogeneous boundary condition at x equals 0, which start from y0 and which reach y1 at time capital T. And moreover, the regularity of the trajectory is this one, so it is in the Jouvray class G1 lambda. Okay, so this is a local exact controllability result. And so we can apply it, for instance, to the good or bad Boussinesq equation. And so let us have now some explicit application of this result. So you consider the good or bad Boussinesq equation. We have a result for both, actually. And so typically at x equals 0, you consider these two homogeneous boundary conditions. Okay, you can. And at x equals 1, you have these two boundary control conditions. So you have two controls, V and W. And here you have two initial data because it's an equation of order 2 in time. And I remind you that when you take plus here, you obtain the Balbucinet's equation, which is severely ill-posed, even for the linear part. So the result is the following. So if R is larger than R hat, if t is positive, there is some number C hat, such that for any pair of function in the space we introduce, which are even. So here the compatibility condition tells you just that your data have to be even with respect to 0. Then you can obtain, you can prove the existence of some trajectory satisfying all the system. And so you obtain also the control V and W in some Chowdhury space. So it's time to give some conclusions. So the flatness approach is a robust method to obtain almost sharp set of reachable states. Almost sharp because with the flatness approach, actually, we had a domain of analyticity which was not sharp. We obtained ball instead of square for the heat equation, for instance. But the advantage is that it is quite general because it can be applied to many equations. And for instance, for the heat equation, the KdV equation, and also it's useful for anisotropic 1D equation. Also, this method gives us some exact controllability result for a sublinear parabolic equation and also for anisotropic nonlinear equation, even if they are not well posed. So that's also interesting because I remind you that in the classical approach, we need the equation to be well posed in time to apply a fixed point argument using, for instance, the contraction principle or Schauder's method. And also it is useful to design efficient numerical method. So you compute just partial sum instead of the infinite series. And your partial sums give you some good approximation of both the trajectory and the control. Okay, that's all. Thank you for your attention and thank you for your patience.
Yes, I have a question concerning the controllability result for the nonlinearity equation. So my question is the following one. With your result, can you also handle some parabolic equation that lead to blow up without control? Can you prevent the blow up from happening with the control or not? I have not really.
Well, I don't know. In general, you have blow up when you are far, or the blow up is for some time when the initial data is large enough. Our result is for small data. So for small data, if the data is sufficiently small, actually, you can say that the blow up will not occur before some time capital T. So as our result is local, difficult to say if we can prevent the blow up.
Okay,
but that's the same concept for with any local result, actually.
Yeah, but perhaps I have missed something. There is one slide where you can solve, let's say, a parabolic semi-linearity equation. Yes, can you go back to some slide just to
yes, let us try.
Yes, so the first method of the proof, yes, here, the first step consists in studying a Cauchy problem, okay? And
yes.
The initial data here could be large in the first step or not?
No.
It is small. Okay.
This is expressed here. So this is this theorem. But here we assume that the derivative of G0 and G1 are abundant this way with some C, and C is small, of course.
Okay. Yeah. Okay.
C is expected to be small. That's the reason for which you have a global solution. If C is large, I cannot say anything.
Okay, thank you. Yes, thank you very much.
You're welcome.
So when you show the reachable space for the heat equation in the interior control case, you have shown some results. For the KdV case, you have shown from the boundary control. But if it is a interior control, is it anything known for the case by this method, the reachable space?
No, you're right. We didn't apply yet the flatness approach for the reachable states of KDV with internal control, if it is your question.
Yes.
It was not done. No, it's for me, it's open. It's open.
Okay. And usually this kind of interior control case, a flatness method other than the parabolic equation is not used. Is it used? Means the flatness approach for interior control purpose?
But to my best knowledge, the only thing which was done was the work with motion about reachable state for the heat equation, but it was not applied for general parabolic equation to my best knowledge. No, for the distributed control, I mean, it's still open as well.
Okay. And the thing, like on the first lecture also I have asked you, like here we saw that the number of the derivative in time n is less than, strictly less than number of the derivative in space.
Yes.
N is strictly less than m. So in the approach with n equal to m, like transport and heat equation case, transport and wave equation case, where is the difficulty arises in the sense of regularity? Is it the difficulty?
So I had some questions similar to this one, I think, is the first talk. So for transport equation or wave equation, where we have the same kind of derivative, the same number of derivative in time and space, is still open. It's completely open. It has to be done. What we expect that actually probably you should be able to prove exact controllability result in space of analytic function, provided that you allow some provided that the control time is large enough. This is what we expect. But although it has to be written, I didn't know any clear proof of that. It has to be done. The only contribution I know is I said so some work by Michel Fliess and collaborators in 2000 something, where they prove, I think, approximate controllability for the wave equation. So it was approximate controllability, but for exact controllability, I don't know any result in this direction. It has to be done.
Is it for the steady state in the wave equation, what you are saying?
Can you repeat?
Is it for the wave equation, what you are saying, the result, only result in 2000? Is it corresponding to steady state?
I think it was for the wave equation. Yes. If you send me some email, I can give you the reference. I can go back and find the reference and give you the reference. I think it was for the wave equation. Yes.
Okay. Thank you.
You're welcome. Thank you for your attention.